Okay, so in this example problem, we're going to be determining the net hydrostatic force on a triangular door. And this triangular door is an access port for this form here that contains some oil. So this problem is very similar to some other hydrostatics problems that we've done in the past. So I'm going to kind of breeze through some of the assumptions, some of the algebra, some of the calculus. The real novelty here is the integration over this triangle and how we actually do that. We're trying to find the resultant force on the port due to the oil in the atmosphere. This is our port, here's our geometry, we have our standard assumptions for hydrostatics problems, and we'll start with the first step here, determining what the equation for these two lines is. And the reason we need to know that is because we need to integrate between this line and this line. So we're really just using y equals mx plus b and the geometry given to determine the equation for this line and the equation for this line. And again, the side view of this access port is as shown on the left, and then if you look at a front view, it is this view on the right, and again, it is just that triangular shape. Here are the equations for the lines. Feel free to pause and look at this as you will, but we're going to just kind of breeze on to the next step here. So here we're just using the hydrostatic pressure equation as we usually do, and we're integrating the hydrostatic pressure equation over the entire triangle. So we're taking our hydrostatic pressure, which is P infinity plus rho GH, subtracting from that the pressure due to the atmosphere, because again, if you kind of look at a little differential area element just like this, you'll have your P here, which is just due to your oil, and you'll have your P infinity here, which is just due to the atmosphere. So your net pressure is that P minus P infinity, or in other words, rho GH in this case. We're going to take that net pressure, or that rho GH, multiply it by the differential area, which in this case would be this area right here. And we're going to, again, integrate that product of P net and dA over the entire area A of the triangle. Now, there are two approaches you can take here for determining your differential area dA. You can do this with multivariable calculus, or you can do this with single variable calculus. Both of them involve a decent amount of work, but the single variable calculus is a little bit more accessible just from an academic perspective. However, what you end up doing here is, if you look at the multivariable calculus approach, you end up having two differential measurements that you need to deal with, dx hat and dy hat. So here, if we look at a little dA and we make it kind of shaped like this, where we have this dx hat and dy hat, we're going to have to do a two-dimensional integral to integrate this little element over this entire triangular surface. Now, what we can do alternatively is make a larger differential element in width. So we have a differential element that is just dy hat in height, but a finite value w in width. And then our differential element, instead of dA equals dx hat times dy hat, it's dA equals w times dy hat. So this is actually a one-dimensional differential element. This is a two-dimensional differential element. So this one-dimensional differential element will only require a one-dimensional integral, but we make up for it in the complexity of the algebra we need to do in the integrand. And we'll show that in both cases. And then the third case is we can just use a shortcut to kind of bypass this integral entirely if we remember what the definition of the first moment of area is. And we'll also go over that briefly. I'm going to just kind of, again, breeze through some of this calculus. I'm going to make separate videos on how to perform these integrals more properly. So really, this is just going to be some calculus and algebra on the screen for you to pause and review and study for yourself if you'd like. Please keep that in mind. So as we're going on to the next slide here, we're going to first start with the multivariable approach, where we have this differential element of dx hat and dy hat. So we have a two-dimensional differential element, so to speak. And again, you can kind of see here how this works. We have the oil pressure on one side, the atmospheric pressure on the other side. So the net pressure, P net, is P minus P infinity, or in other words, rho GH. And if we integrate rho GH times dA over the entire area A, and we have a differential area that is of dx hat, dy hat, we have this two-dimensional integral right here that results. So the integral from 0 to a, which is the integral from this point right here to this point right here, integrating the integral from x1 hat y hat to x2 hat y hat, which is integrating from this line to this line. So essentially what this is saying is integrate my little differential element right here from this point to this point and this line to this line. And if you do that, you'll have differential elements that fill up this entire triangle. So this is what this two-dimensional integral ends up looking like. Here are the equations for the lines as a reference. And again, we have our triangle written out in a custom coordinate system x hat and y hat as shown right here. So if we perform that integration on that double integral, this is our result for our net force. It is the quantity rho GA squared B over 3. And again, I'll just leave this on the screen for a moment for you to study as you wish, but I will create a separate video going through this math a little bit more in depth. So now we have the single variable approach. So in this case, we have a one-dimensional differential element, so to speak. And what I mean by that is A one-dimensional differential element just has one differential dimension. A two-dimensional differential element has two differential dimensions. A three-dimension differential element has three differential dimensions. So this is a one-dimension differential element, so we only have one differential dimension, dy hat. And then we have a finite dimension, w here. And essentially we have the same logic. We're integrating the net pressure over this area, except now instead of dA being dx hat dy hat, we have dA being w dy hat. And since we only have this dy hat instead of dx hat dy hat, we can get away with a one-dimensional integral. And at this point, we only need to know what w is. Well, w is just the width of that differential element at any given location. So it's really just the value of this line minus the value of this line. So that's our w. And keeping that in mind, we kind of conserve complexity by making that algebra harder, but we only have to do a one-dimensional integral. Here's the math for that one-dimensional integral. And you will see that the net force, or FR, is again the quantity rho GA squared B over 3. So we get rho GA squared B over 3 for the single or the one-dimensional differential element case, and we get rho GA squared B over 3 for the two-dimensional differential element case. So those agree as they should. And then we have approach 3, which is the shortcut. Now, this is only if you could remember the definition of the first moment of area. And the first moment of area basically says the integral over a of x dA is xCA, or the integral over a of y dA is yCA. And what you can see here is if you write out the equation for FR, so it's the integral over a of p net dA, and we've determined that p net is just that rho GH, what we end up getting is the integral over a of rho GH dA. If we just stop here, we don't draw any differential elements, we just stop here, and then we move on to the next slide and we say, well, the integral over a of rho GH dA, that's just rho g times the integral over a of h dA. So what we have here is our custom coordinate system, x hat, y hat, is such that y hat is basically equal to h. We know that h is positive down from the free surface, and we have drawn y hat such that it is also positive down from the free surface. So with that being said, if we go back to where we were, we see that rho g times the integral over a of h dA is really just equal to rho g times the integral over a of y hat dA. Now this quantity right here, the integral over a of y hat dA, that is the first moment of area about the x-axis, as you can see here. So that is just equal to y hat CA, and that's where we get this quantity right here. So this integral is equal to rho g times y hat CA. And then we just need to know what the y hat coordinate of the centroid of that triangular area is, and we know what the location of the centroid is within a triangle. It is b over 3, h over 3 for a single right triangle. We extrapolate that to a double right triangle, so to speak, a full right triangle, and we get this final result right here, which is again, the numerator is the quantity rho GA squared B over 3, which agrees with the one-dimensional case, the one-dimensional differential element case, and the two-dimensional differential element case. That's exactly as it should. So we have three different methods that are showing that the resultant force is equal to this quantity right here. And now the only thing left to do with this resultant quantity, this resultant force, is to find out where it acts. So now we just need to determine what the location of FR is. And to determine the location of FR, we need to, as it says here, equate the overall moment about each axis with the summed distributed moment about each axis. So what that's essentially saying is we have a pressure distribution on this door here. And so about each axis, we also have a moment distribution on this door here. And this overall force FR needs to be applied in a location such that at that location, FR creates an equivalent moment to the distributed moments about each axis. So in math, about the y hat axis, that translates to FR times some distance x tilde is equal to the sum of the moments about the y hat axis. And about the x hat axis, that translates to FR times some distance y tilde equals the sum of the moments about the x hat axis. And that's where this comes from. And again, keep in mind that this FR is applied perpendicularly to the door because the pressure distribution is also perpendicular to the door. So again, this is a lot of math. I'm going to kind of breeze through this. So I'll just leave this on the screen for a moment for you to follow as you wish. But this is essentially just the follow through of this integral right here. And this integral is very similar to a bunch of integrals we've done in the past, including the other integral we've done for FR already in this video. So I'm just going to leave this on the screen for a moment. Feel free to follow along as you wish. There's nothing crazy going on here. It's really just a lot of algebra and a two-dimensional integral, as you can see right here. So this is the final result for what is essentially x tilde, the distance from the y hat axis, and the x tilde value is equal to just b over 2. And now going on to the next slide, we see the same process about the x hat axis. Again, we're just equating the overall moment with the sum of the distributed moments. Same kind of calculus, same kind of algebra, a lot of complexity here. And you get that the y tilde coordinate is 3a over 4. So in summary, we are given that a is equal to 2 feet, b is equal to 1.5 feet, rho is equal to 875 kilograms per cubic meter, which is the density of crude oil. And we found through calculation that FR is equal to the quantity rho GA squared B over 3, X tilde is equal to B over 2, and Y tilde is equal to 3A over 4. Combining these givens and these found, we find that the resultant force is equal to 486.6 newtons, X tilde is equal to 0.75 feet, and Y tilde is equal to 1.5 feet. So what this is saying is if we apply FR at a distance Y tilde down in Y hat and X tilde over in X hat, then that FR creates an equivalent system to the distributed pressure system that we actually have in the physics. So in other words, this FR creates an equivalent force to the distributed pressure, and this FR creates an equivalent moment about the X hat axis and Y hat axis, as does the distributed pressure system. So this FR at this location is an equivalent system to the distributed pressure system that we actually have in the physics. And this FR at this location is just a much more convenient way of thinking of this problem and talking about this problem than the actual distributed quantities that we have when we talk about hydrostatics. Okay, so that should be it for this video. I really appreciate you watching. Thank you very, very much, and I will see you next time.